From the second we first looked up at the stars, we've been completely obsessed with one question: where are they going next? It's an obsession that connects a mysterious, gear-filled device found in an ancient shipwreck to the supercomputers that are guiding today's space missions. So let's dive into this incredible 2,000-year race for cosmic precision. It all kicks off with a totally chance discovery. Back in 1900, some divers were exploring a Roman-era shipwreck off the coast of this little Greek island, Antikythera. And amidst all the usual ancient stuff, they found something that just shouldn't have been there. It was a lump of corroded bronze that was about to completely rewrite the history of technology. Because inside that corroded lump was an absolute marvel, a series of complex, interlocking gears. This was the Antikythera mechanism, a device so sophisticated, so advanced, that for decades people thought it had to be a hoax. It was an analog computer, a literal clockwork model of the cosmos, designed to map the heavens with just breathtaking accuracy. Okay, so to really truly grasp how incredible this machine was, we need to put it in the context of its time, and that's where this story gets even more fascinating. This timeline right here reveals something just astonishing, a massive, massive technological gap. The Antikythera mechanism was likely built around 200 BC, but after it was lost to the sea, humanity wouldn't create anything even close to its complexity for another 1,400 years. It was literally a piece of the future lost to the past. So, how did this ancient computer even work? Well, with a simple turn of a hand crank, you could set a date. The intricate gears would then whir into motion, moving a series of pointers that would predict the positions of the sun and the moon, the timing of eclipses. It even tracked the 4-year cycle of the Olympic Games. It was, for all intents and purposes, the very first machine ever built to solve the orbit problem. And that fundamental idea, using a physical machine to solve a really complex math problem, it didn't just vanish forever. It just went dormant, waiting for centuries to pop back up in a totally new form. Okay, let's fast forward nearly 2 millennia to the 1930s. At MIT, a guy named Vannevar Bush creates the differential analyzer. It's a different machine for sure, built for a different time, but the core concept is identical. Instead of bronze gears tracking planets, it used mechanical rods and wheels to solve the kinds of complex equations needed for modern engineering. And get this, an early version was even built using mechanoparts. It's just a perfect testament to the power of mechanical computation. And the evolution didn't stop with mechanical bits and pieces. By the time we get to the space race, the concept had leaped from gears to circuits. This is a real NASA diagram from the 60s. It shows an analog electronic circuit. It's not designed to track stars, but to calculate the temperature of an orbiting spacecraft. The tech changed, but the principle? Exactly the same. A physical system modeling a mathematical reality. Today, though, we've moved way beyond those analog devices. We're deep in the digital realm now. And with that massive shift, the complexity of the orbit problem has just exploded. Okay, so don't freak out about the equation. You don't need to be a mathematician to get this. At its heart, the orbit of a satellite around the Earth should be a simple, predictable path. But in reality, it's a chaotic, tangled mess. And the reason for all that complexity comes down to a series of tiny, but really disruptive forces. These disruptive forces are called perturbations. That's the AP term in the equation. They're all the tiny, chaotic influences that throw a perfect orbit completely off course. For instance, the Earth's gravity isn't perfectly the same everywhere. There's also this faint atmospheric drag, even way up in space. And of course, the gravitational pull of the sun and the moon are constantly tugging on the satellites. Now, each of these forces is tiny on its own, but over thousands and thousands of orbits, they add up, they accumulate, and they create massive uncertainty. Accurately predicting these orbits is so critical that scientists are in this constant race to find the fastest, most precise ways to calculate them. And that brings us right to the heart of a recent study that basically pitted several different computational methods against each other in a head-to-head competition. So I want you to imagine a race with 6 different competitors. Each one is a different algorithm, what's called a numerical integrator, and each one is designed to solve that complex orbit equation. We've got the adaptive sprinters, a high-order specialist, an old-school classic called GJ8 that's been a workhorse since the 1960s, and a brand-new challenger called APC.
So, how do you pick a winner in a race like this? Well, the key metric is something called work precision. It's actually a pretty simple trade-off. Can you get the most accurate answer, that's the precision, while making your computer do the least amount of work? The best algorithm, the winner, is the one that masters both accuracy and efficiency.
The researchers put these 6 algorithms through their paces, testing them across 4 different types of satellite orbits. So, who came out on top? All right, let's look at the results. This chart shows a standard low Earth orbit. The line going down and to the left is better. It means less computer work for more accuracy. And as you can see, that new challenger, APC, is way out in front. It delivered a highly precise answer with far, far less effort than any of the other methods. It's not even close.
And the difference gets even more dramatic when we look at a highly elliptical orbit. This is a much tougher problem to solve. Here, that old classic GJ8 really struggles. It needs a huge number of calculations to get the job done. But APC, it stays incredibly efficient, once again requiring the least amount of work by a long shot.
You don't have to take my word for it. The researchers' conclusion was totally unambiguous. As they put it, one obvious conclusion is that APC performs better for almost all the test case orbits. So, in this race for computational efficiency, the new challenger was the clear, undisputed winner.
Okay, so a new algorithm proved to be the fastest and most efficient. Big deal, right? Why does this super technical competition matter to the rest of us? Well, because this abstract math is the invisible engine that powers our entire modern world. Every single time you use your phone for directions, you are relying on hyper-accurate orbital predictions. The weather forecasts you check in the morning, the global communications network that connects all of us, it all depends on knowing exactly where our satellites are at any given moment. And as space gets more and more crowded, this science is what prevents catastrophic collisions between satellites and space junk. It is absolutely fundamentally critical. From ancient bronze gears to analog circuits to these hyper-efficient digital algorithms, the tools we use have evolved beyond imagination. But the fundamental quest, it's exactly the same. We are still the same people looking up at the sky, trying to predict the future with ever greater precision. And it just makes you wonder, what incredible tools will our descendants be using 2,000 years from now?